Hi everyone. In this video, I will cover on the matrix algebra. The introduction part, I would say, is just a refreshing learning video before we go on the content of the matrix algebra for the degree level. So the introduction of the matrix algebra at this video is actually just to refresh on what you have learned during school time and during matric times. Okay. Alright, matrix algebra, let's look at week 6 first. The topic on matrix algebra for non-homogeneous linear algebraic system. In this video, we will look into the introduction part first, 6.1. 6.2 we will cover during Thursday class. Okay, before we start, matrix is, once again, matrix is a array of mn element where m and n are integer. So this is important, they are integer, and also m represent the row and n represent the column. And the difference between matrix and column and row vector is shown in the table 6.1. So again, the matrix format are not just in a scalar thing. It can happen in the vector as well. The only difference between the column vector and also the matrix is on the notation and also the bracket that normally we use. So commonly when we are dealing with matrix, we are dealing with the square bracket like this. And when we are dealing with the column vector, we are dealing with actually the curly bracket. Curly bracket like this. Okay. And the row vector, as this is the column vector, this is the row vector, and again they use the same notation as the curly bracket. Okay, so the square bracket here we normally use for the matrix. Okay, where m and n is the element of the matrix, where we have the m row. This is the row 1, 2, 3 and 4, which is the horizontal line, and also the vertical line is the column of the matrix. Okay, the common notation of the matrix and vector are shown in this table, the table 6.2, where normally when the matrix we form the matrix, we put it as the non-italic and bold, and also we use the square bracket like this. And if it's vector, we normally italic it and make it bold, and we use the curly bracket. Okay, symbol will be also will have the curly bracket like this, and it is italic. Italic. Okay, and the matrix format is just a normal box format of the matrix like this. Okay, all right, let's look at the types of matrix to refresh back on what we have learned during school time. Number one, the first type of the matrix is the null matrix, meaning that all the element in that matrix belong to 0. The example shown here is actually the 3 times 3, where you have the 3 row here, and also the 3 column here. Symmetric matrix, meaning that the element of Aij is equivalent to Aji. So let's put it this way. Aij, let's say my row is third row, and also I'm looking at the first column. So meaning that this is the third row and first column, so element of 2, which is equivalent to the Aji 1, 3. First row, column 3. This is first row, column 3. That's what you mean by that. So if you have the matrix that has this element, A31 equivalent to A13, or A21 equivalent to A12, so this is what we call the symmetric matrix. Okay, diagonal matrix, meaning that you only have element at the diagonal matrix. All element of the main diagonal are equal to 0. And the identity matrix, as given in this, where you have a same as diagonal, it's just that a unit matrix here in the middle, that element here is all equivalent to 1. So upper triangular matrix, meaning that at the bottom, the 3 bottom at the corner bottom here, all elements belong to the 0, and the lower triangular matrix at the upper side is 0. Banded matrix meaning that all elements 0 except for the band center on the band diagonal. Okay, and the trigonal matrix meaning that we have the trigonal 0 here at the bottom and also at the top part. The skew symmetric matrix or anti-symmetric meaning that at the element aij like this, instead if it's symmetric, aij will be equivalent to aji, but here aij equivalent to negative aij. So for example, I have like a23, meaning that row 2, this is row 2, element 3, which is number 3, equivalent to a32 row 3 column 2 but negative of it here. So that's why this is what we call the anti-symmetric or skew symmetric matrix. Okay, all right. Now we look into the basic operation of the matrix. Okay, trace of the matrix is the summation of the diagonal element, 4 plus 9 plus 0, so you get 23. I mean, imagining that the matrix is given as this. Okay, equality meaning that if you have the same matrix that has the same element in and also the same size, number one, it must have the same size, same size of f of mn, and also has the same element. Okay, so we can say that the matrix are the same, but if the two matrix are not the same size even, and also different element, so we can say that the matrix are not the same. Okay, all right, looking back, tracking back at the matrix A and B here, if we want to find the additional of matrix A plus B, we can add element one by one. 4 plus 4 you get 8, 13 plus 13 you get 26, negative 2 plus minus negative 2 you get negative 4, 19 plus 19 you get 38. Okay, however, A minus B, same concept, it just that now you minus element by element. 4 minus 4 you get 0, 13 minus 13, 13 minus 13 you also get 0, negative 2, minus will become plus, you get 0, and also 19 minus 19 you get 0. Scalar multiplication, let's say you want to multiply one scalar, here the scalar here is equivalent to 2, you multiply with the matrix D here, so each element inside the matrix D you multiply with 2, and then you will get this. Transpose of the matrix, I hope you still remember. So if you have a matrix that has the same has this size, one particular size, for the mn here, where here let's say for this case the m is actually 2, and the n is actually the column got 3, so it's 2 times 3 here, but when you transpose it become 3 times 2, here become in front, 3, 1 2 3, and then 2 column. Okay, all right. I hope you still remember matrix multiplication. You multiply here to here and so on. Okay, so you will get this part, and the matrix can only be multiplied if the matrix can only, let me do it once again, this one multiply this one. Okay, but first thing first, before you want to multiply the matrix, you need to check the size. Okay, so this is 3 times 2 and 2 times 2, so if it has the common number here for n, n at the first matrix, and then m at the second matrix has the same common number, then you can multiply it. The answer will belong to m at the first matrix and n at the second matrix, which is 3 times 2 in this case. Okay, So from here 3 times 5 plus what is it, 1 plus 7, and then you get 27 plus 2 here, and then here is 8. Okay, 8 plus 5 multiply by 5 plus 6 multiply by 7, and then 8 multiply by 9 plus 6 multiply by 2. Okay, and then 0 multiply with 5 plus 4 multiply with 7, and 0 multiply with 9 plus 4 multiply with 2. So at the end, that is why you get this answer. 15 plus 7, 22. 27 plus 27 plus 2, you get 29, and so on. Okay. Alright. Determinant. Okay. I hope you still remember what is determinant. If you have 2 times 2 matrix like this, determinant is these two. You multiply in together, and then you minus with this. Okay. So 4 multiply with 4 multiply with 19, and then negative 2 multiply by 13. You minus it, then you get the determinant. Determinant can also be calculated using calculator. Please make sure you know how to calculate it using calculator, and don't make your life difficult during the exam later on, because you need to do it fast. Okay, of course the concept on how to calculate the determinant you need to know, but then again it can be directly automatically calculated using your calculator. If you don't know how to use calculator to find determinant, please just Google finding determinant using calculator. You insert in your model, and there's a lot of video available on YouTube how to insert in the matrix and then directly get the determinant, cofactor, adjoint, and so on. But again, this video just to recap on what you had covered and you have learned during school and matrix. Okay, so if let's say determinant is in terms of 3 times 3, again you can take this one and bring it outside, and then you handle this one, and 19 here, 19 multiply with 0 minus 2, and then negative 13, leave it with negative 2, 3, 1, and 0. So that's why it become like this. And plus 3 here. So this is, if I can erase this part once again, for this part, this is row 3, and then, row 1, column 3. So you just leave it with this matrix, and you put it here and find its determinant. Okay. Then you expand it like 19 minus, like this one, 4, 0 minus 2, minus 13, and then 0 minus 3 plus 3, negative 4, minus 19 multiplied by 3. So you will get the answer is negative 152. Similarly, if you have a bigger size of the matrix, like this one is 4 times 4, the notation is the same, 4 here, and then you leave it with this one. Okay, and then this one become negative, this one become negative. Negative 13, okay, you live with this one, okay, and then this one, right, because 13 is here, and then plus 3, so leave it with 1, 2, this column, and this column. Okay, that's why you leave it at here, and then minus 3 at the back. Okay, so when you expand it, you solve the determinant for each 3 times 3 here, and then you can get the answer is belong to 152. Okay, again, if you click calculator, you just insert in 4 times 4 matrix, and you can easily know what's the determinant. But please make sure that you know the theory behind it, how to calculate the determinant of the matrix. Okay, all right, now let's look at the cofactor and adjoint. I hope you still remember that the adjoint is actually a cofactor of matrix A transpose. Let's say we have a matrix A given as 4, 13, negative 2, and 19. Cofactor of that matrix A is you rearrange a bit. So now let me put it here. This is 19, this is 4. You swap position, and then you find the you swap the position, and then at this one you swap the position, and also you make it negative for that. Here, this one you swap position and then negative, you put negative, so now 13 become here negative, negative, negative 2 become positive. So this is the cofactor of matrix A, and a joint is actually cofactor matrix A, and then you transpose it. So transpose now, I hope you still remember, transpose is from here the row now become column. You here, from here, this ray, this direction, 19 and 2 now become the vertical, 19 and 2. Okay, 13 and 4 now, instead of it is horizontal, now become vertical, negative 13 and 4. So this is the matrix transpose. Okay, alright. Cofactor of matrix, okay, that one is just now the example is 2 times 2, easy. But if it's 3 times 3, the cofactor of that matrix, first you take this one, right? The first what you call row and also column, so leave it with 19 and this one, just leave it 19, 1, 2 and 0, this one, so you put here. Then next determinant, now the next one will become this one. Okay, so leave it with negative 12, 1, 3 and 0, negative 1 here, put it here. Alright, and then put negative here, don't forget, again the cofactor for the 3 times 3 you will get like this, like a diamond shape. Okay, what I mean by diamond is this one, the negative is diamond, okay. Alright, so the second one will be negative here, that's why you get negative here. And the last column here, the third column here will be positive once again, follow this one. So at here you will, let me erase once again. Okay, at here you need to close this one and this one. Okay, so leave it with negative 2, 19, 3 and 2, and you do the rest for the second row and the third row. For the second row, how to do it, like this, the second row will be like the second row first column, second row first column, so leave it with 13, 3, 2, 0, 13, 3, 2, 0. Okay, and then for the second, okay, I erase. For the second column, second row, like this, so leave it with 4, 3. Okay, leave it with this. Okay, and you do the rest for that, for the rest, yeah. The third one, this one is the second row. Oh my, sorry, how to undo this? Oh, I cannot undo this, sorry. The second row and third column, so I leave with 4, 13, 3 and 2, 4, 13, 3 and 2. Okay, the first one here, the first column, the third row and first column, so that's why I leave it with 13, 3, 2 and 0. That's why I get this. Sorry, this one and this one, so leave it with 13, 3, 19 and 1, 13, 3, 19 and 1. The second one, let me try to erase. The second one will be the second here, will be the third row second column, so leave it with 4, negative 2, 3 and 1. Okay, and then from here, the third column third row, so leave it with this. That's why you get this. Okay, and then when you solve the determinant for all, you will get this is the cofactor. So the adjoint F is actually the cofactor transpose. Instead of this one, now it become this one. I cannot use this. Sorry. Okay. Now it become this one. Instead of this one, now it will become this one. Okay. So it transpose it. Okay. So the cofactor of 4 times 4 also the same concept. It's just that now the negative is this way. This one positive, negative, positive. It become like this. Let me redraw. Negative, positive, negative, and then it become negative, positive, negative, positive, positive, negative, positive, negative, negative, positive, negative, positive. Okay, that's the sign of this cofactor. Same concept as the first one. If you do it slowly, you will get this as an answer, and the adjoint is actually the transpose of the cofactor. Okay, and then you also learn in school on how to get the inverse matrix. So the inverse matrix, okay, let's say this is the matrix A, which is 2 times 2, 4, 30, negative 2, 19. The inverse of that matrix is 1 over determinant of that matrix multiply with the adjoint A. Okay, so determinant of this matrix A is given as 4 times 19 minus negative 2 times 13. So you will get 102. So that's why you get 102 here. Okay, so the adjoint A is actually this one, transposing this one and then make it negative. Okay, so this is the inverse matrix A. Okay, for the 3 times 3, 1 divided by that determinant, multiply with that adjoint of that of that matrix. But again, 2 times 2 is quite simple to get, but then 3 times 3 you need to do this way. Do this way to get the adjoint of that matrix. Same goes with the adjoint of the matrix G here if you have matrix 4 times 4 in this example. And the augmentation of the matrix is given like this. If let's say you have linear equation, linear equation of multiple variable like this. You have like x1, x2, and x3. This notation of the equation can be transformed into conventional matrix form or augmented matrix form. Same thing actually, it's just that instead of putting it in this way, you can put the dash line here indicating that this is the augmented matrix. There's one matrix missing there, which is the value of x1, x2, and x3 here that needs to be determined in order for the equation to make it equivalent to this column. Okay, so this is the conventional matrix form, and also this is augmented matrix form. This is the normal equation. Normal linear equation. It just has the equation has 3 variables for each, and then we can transform it into a conventional format like this, where we can determine x1, x2, and x3, or we can put it in the augmented matrix form as shown in this example. Okay, alright, that's all on the introduction part of the matrix. I think 6.2 I can cover in week 6 total. In Thursday class. If not, then I will cover in week 7, because week 7 notes not that long, so we can go a little bit slow on that on Thursday and also next week, week 7. Okay, all right, thank you.